Okay, great. So today we proceed our discussion from last time. We only started talking about the proof of MIP star is equal to RE, and I want to remind you again what was the discussion about, and at least modulus on theorem, how do we finish the proof? So if we know this, the thing that I call the compression theorem, how do we deduce that MIP star is equal to RE? And then we will start reviewing the ingredients of this compression theorem. Great, so this is what I said right now, the plan for the talk. Great, so last time I defined this notion of a lambda verifier. I called it only a verifier, but I stated that there exists some lambda such that this runs in at most n to the lambda time, so I just wrote it this time and mentioned this constant lambda in the definition. So a game, again, is 4 sets, a probability distribution on pairs of questions, on inputs, and some decision function that decides whether this is a winning condition or a losing condition for any quadruple of questions and answers. And a lambda verifier is a way to uniformly generate a sequence, an infinite sequence of games. Okay, so instead of just defining a single game, I want to define a sequence of games. And the point is that to generate the nth game, to describe the nth game, to run the nth game in this sequence takes at most n to the lambda time, okay? Time steps, I don't know how to say it. Okay, so the way we do this, the way we generate this kind of a sequence is using 2 Turing machines. The first is called S, and it is called the sampler, and the other is D, the decider. And for any n, for any natural number, Sn just implements the following kind of a sampling procedure. First of all, it tosses some finite number of coins with uniform distribution. Okay, so it gets some sequence of a uniform sequence of some length of bits. And then it does some computations, like it's a Turing machine. So with this input, it does something. And the output is a pair of questions. So 2 strings. And the point is that you can bound the length of these strings by the running time. So you know that actually these are not just any 2 strings. These are 2 strings coming from strings of bits of length at most n to the lambda. Okay, great. Clearly the n is only from 2 and so on, right? So the case of n is equal to 1 is now, I disregard it. The uniform generation is only from 2 and on. Okay, so this is the way that we have like a Turing machine that pushes forward the uniform distribution to some other distribution on questions. And for any number n and any quadruple of sequences, x, y, a, and b, this dn needs to run in at most n to the lambda time. If it outputs 0, we say that for example, accepted, and if it either outputted anything else or outputted or never outputted in the time that it was given in n to the lambda time, we say that it didn't accept. It rejected this.
Michael, the way it's written now, there is no. It's not clear what n does. I understand what n to the lambda.
Yes, you are right. Lambda has. I didn't say lambda has another role here, and it is not written here. But the second role of lambda is that the description of S and D is bounded by lambda. So if you take the length,
no n. There is no role for n.
There is. This is exactly what I said now, Nati. You want to bound 2 things: the running time, okay, which I claim is n to the lambda, and and you can say that now n is not important, but the point is that n to the lambda is a bound on the running time, and lambda is a bound on the description of S and D. And now you get a sequence. Now the seventh game, you know that it has only 7 to the lambda time steps that Turing machines can do on at most 7 to the lambda time steps.
Wait, Nati, and also
maybe I'm confused.
If I'm wrong, n is the input to the sampler and to the decider.
Okay.
This is the nth game.
Okay.
Yeah, so this is the role of n.
No, but hey, where is n here? If you told me that x and y if you sample n bits of then I'm fine. And you run in time and to the lambda, that's okay. But where is n?
Yeah, you run in time n to the lambda.
No, but where is n? What role does n have? You know, if instead of n to the lambda I called it w, why are there 2 parameters? I only see the role of n to the lambda. I don't see the separate role.
Okay,
of
the nth game, but you want some bound on the running time of the nth game, right, Mati?
I have a question that maybe answers the question. The push forward depends on the n?
Yeah, clearly, yes.
So this is the role
you
of
toss
n.
more and more coins when you play a larger and larger game. Yeah, you have potentially more and more questions.
No, I understand. If you told me that you take a string of length n and you proceed from there, then I have no problem. But you don't bound the length of the string.
Yeah, the
I don't see. You know,
the input to S, Nati. The input to S. Okay, there is no input to S. The S just outputs a pair of questions by some distribution which is a push forward of some uniform distribution on a set which is defined also using n, clearly, like the size of the number of coins that I toss at the beginning of S depends on n, for example. And S of, I don't know, like I just want some connection between the index of the game and the running time of the polynomials the running time of the Turing machines that I have here.
Okay, let me try one.
Maybe you can give an example.
Shut up.
Maybe you can give an example.
Just in a moment. I'll let Nati ask his.
A simple example is just pick an SN just takes n coin flips or 2 n coin flips, sends one to them. But it can do something more complicated. It can use n squared and do some calculation and then output something of length squared of n to each or whatever. Everything should be bounded by, that's all.
Then you should divide lambda by 2. This is...
No, the running time might be complicated. To compute what to send could take you a lot of time.
We will see an example today. So hopefully in just a few moments. I don't want to give it yet because there is some motivation to this.
Maybe another connection is that it says that the distribution is on 0, 1 star, but really it's on 0, 1 to some polynomial in n, right?
Yeah, this is true. And not some polynomial. We gave the specific. Beforehand, give me this lambda, give me this number, and then I know all the IA, IB, OA, and OB, and we know the running time, and we know everything. Like everything is actually finite, and this lambda defines the size of these things. Okay, anyway, this is, you do agree that this generates games with the...
Absolutely. The only thing is I'm still not convinced that we need 2 parameters. If you, instead of 0, 1 star, you wrote 0, 1 to the n, I'm perfectly happy.
Okay, but then I will not have a game for each n. Okay, so I will have just games for some n's.
No, for each n, there is the input is 0 from 0, 1 to the n. You feed them n bits, and then they start sampling and checking and deciding and so on.
Okay, yeah, I need to think about it. I'm not convinced, but what? Yeah.
They need to do all of this in polynomial time.
Right.
So n to the lambda is the polynomial bound.
But then it's not 0, 1 to the star, it's 0, 1 to the n. That's okay, I'll shut up. It's okay. I mean, go ahead.
I think he wants just a sequence of games, and you need a number for each one of them.
Okay.
It just makes it more convenient, I think. I'm not sure it's so necessary to decide.
Yeah. Okay, great. But the point is that actually you can think of the nth game generated by these two Turing machines. So you can just input n in S, input n in D, and then dn, if you put in X, Y, A, and B, decides whether it's a winning or a losing condition. And we can, since we had this time bound on these Turing machines, we can say that we actually take only strings of length n to the lambda at most.
Okay.
Great. So let's go move along. Now I want to state the theorem. Well, why did I lose? I lost one slide. Great, compression, sorry. Okay, so what compression means? So this is the main, you should think of it as the main theorem of the MIP star is equal to RE paper. And it states the following. So for any nice enough lambda verifier, and nice enough is just saying something about the way the sampler works. Okay, there's something called conditionally linear maps, and we need the sampler to work with such, and then this is a nice enough lambda verifier. There are some other technical conditions, but really nice enough is not such a hard thing to satisfy. So given such a thing, we can generate a new lambda verifier. And last time, Livio, you asked whether this is the same lambda. So actually you can take an even smaller lambda, but if you take a smaller lambda, not all the conditions are satisfied. But if you take the same lambda, you can say that all the following conditions are satisfied, okay? Such that the following holds. So you generate a new verifier, so a new sequence of games, and I claim only things about the entries of the sequence that are powers of 2. So the claim is the relation between the sequence, the new sequence, and the original sequence where the inputs are powers of 2. So we claim that if the value of the games of the 2 to the nth game to the original verifier is 1, then the quantum value of the new game at the end point, at the nth entry, is also 1. Okay, so this is like a completeness result. It preserves the perfect, if you can play in a perfect way the 2 to the nth game, you can play in a perfect way the new nth game. Similarly, there is some soundness condition here. So if you cannot play very well, where very well is more than 1/2, the 2 to the nth game, you cannot play very well the new nth game. So in this sense, last time we called this V prime some simulator. We said that it simulates the nth game of V prime, simulates the 2 to the nth game of V. And it simulates in at least in this sense, in the sense that it preserves a perfect value, and it preserves a low value. And lastly, and this is a point where Michael gave a good explanation of this point last time, the amount of entanglement needed to win the nth game, the new nth game, with at least probability 1/2, is bounded from below by either 2 to the 2 to the n, like the maximum between 2 to the 2 to the n, and the maximum and the amount of entanglement needed to win the 2 to the nth game, the original 2 to the nth game, with probability at least 1/2. Okay, so it means, so at least the heuristics here is that you pay with more entanglement. The provers use more entanglement, and by using more entanglement, they can reduce the running time of the original verifier. So in this sense, it compresses. Any questions about this compression theorem?
Michael?
Yes.
Intuitively, I would have expected the last claim to be with the opposite, to the claim of a Vn prime to be lower than, not greater than. Because if you want to simulate
the what? Eyal, please.
The entropy
amount
claim.
of entanglement?
Yes, the entanglement claim. I'd expect that you would say to simulate this game, the simulator needs not too much entanglement. And here say you give a lower bound for the resources
you need a lower bound. So I'll explain it. I'll at least wave my hands a bit and try to explain where this comes from. The point is that the way that they do this compression is you have, for example, a protocol to solve some like 3 coloring of a graph, okay? And then I tell you that you were in the first talks, you take the succinct 3 coloring of a graph, or the succinct 3 coloring of a graph. And then the point is that you want to use the previous protocol, but the problem is that your questions and answers are too long, okay? But you can do the following. Instead of asking the provers the original questions, you can ask them shorter questions and ask them to sample the long questions. So you want to ask short questions, and you want them to, using the short questions, sample some long questions. But for them to be able to sample the long questions, only using the short questions, they need more entanglement. You can, like the way they do it is that the provers now need to use more entanglement because they need to sample some longer thing. We will see it in a moment, but
I understand why would the entanglement will be larger for V prime. What I don't understand is why do you need this? Why do you give a lower bound for this entanglement? I'd expect that for this claim to be strong, interesting, whatever, you'd give an upper bound, because if you want to say,
so you will see in a moment. My claim is that this proves MIP star is equal to RE. So you will see in a moment where I use the lower bound. So
okay, so
you will just see it in a moment.
Perhaps this will come with the intuition.
Yeah, I don't know if it will come with an intuition in the sense that you will understand why this is true, but at least you will see how is it used.
Third condition, what I'm trying to say is that the third condition does not agree with what I think of when you tell me it's a simulator. Because when you tell you,
I think Michael Benor gave a good intuition about why you would expect of paying some price, and this is like the price. But
no, you actually, sorry, you actually want to say that you really need to use this price in order to, that's what will prove our theorem. You're right that the simulation will not use more than that. So you, in a sense, what the proof will show is that we actually get some almost equality here. But
what I'm saying is that you give here, you tell that you can have a bed simulator in the terms that it needs lots of entropy. But if you give me a simulator, I'd like you to tell me how good it is. Not how bad it is.
Proving.
I had the same complaint last time, and I still think that you should write before 3. However,
okay, so let's see how without the however these 3 conditions prove the result.
Wait, just a second.
Hi, everybody.
If all you want is to show that you have this amazing condenser, then then this condenser is still amazing. However, it needs more entanglement. But if what you want is to separate 2 classes of correlations, then it works in your favor, because
exactly.
So this is not supposed to be a claim about how good a compressor can be.
It doesn't say that this is the optimal. This doesn't say that this is the optimal way of compressing Vn. You are correct that there is no optimality of this V prime. You can say, like Nati is trying to claim here, that the third condition is a bad thing. But we will use this bad thing, this bad behavior of V prime to our favor and not to our, for us, it will be good.
Okay, thank you.
I think this is actually this is clearly what should be proven, because the problem is that, okay, suppose we have two provers that use a few qubits. Then we can find the strategy simply by enumerating over all possible strategies, or just taking a net over all possible.
Right. We spoke about this idea. And,
Exactly. So what we need is actually to force the provers to use more and more qubits, right? So this is exactly what we need, right? We don't want simple games. We want to answer Nati's question. Can't you just put a bound on the number of qubits that the provers need, right, Nati? This is what you asked last time, right? So
maybe 2 times ago.
You can't put a bound because it can go faster than anything, right? And then you can still have a game that is described by a constant number of bits and requires more and more qubits. So therefore, you can never stop and say, if I haven't found a strategy so far, there's no strategy.
Yeah. So what Amnon is saying is that you cannot hope that the entropy will not grow, right? Because then you would be able to solve RE in some bounded time.
Right.
But also it works in our favor because we want to show something that can be done with infinite dimensions that cannot be done with finite dimensions.
Yeah, this is exactly the point. But I think this is an important discussion, but I prepared at least like a motivation to this discussion. So maybe let's go through it and then go back to the discussion, because I think it will help us. So the point is to show now that this previous theorem, this compression theorem, actually proves that RE is in MIP star. And the way we do it is that for any Turing machine, we will show that we can decide whether it halts or not, if we can decide whether the value of the game is greater or equal to 2/3, or in this case, lower or equal to 1/2, okay? So the separation between 2/3 and 1/2 is enough for us to decide whether any Turing machine halts. And the way we did it, we talked about it a bit last time, but it was at the end of the talk, is that we define the following. So there is a way to define, and this is not this is an informal way of defining it. There is a formal way which describes why this is even definable. But for any Turing machine, you define this verifier, and the lambda of the verifier depends on the Turing machine and is computable in polynomial time. So this is a lambda verifier. The lambda depends on M, and the size is polynomial in the size of M. The time to compute this M is polynomial in this lambda is polynomial in the description of M, such that the following holds. So the way the verifier acts is the following. It just simulates the Turing machine up to the nth step. So the nth decider just simulates M n times. And if it halts, it accepts. So this is the easy part. But the otherwise, the more complicated thing, then if it didn't halt, it takes the description of itself, it does the compression on itself, and it plays the same game. So the same position of game, the nth game, using the same questions and answers. So as we discussed a bit last time, it's like saying something like simulate M with n steps, and then simulate n with 2 to the n steps, and then simulate M with 2 to the n steps, and so on. But in a way that is bounded in time, and since we have a uniform lambda here, actually there is a fixed point to this iteration, and everything works. So I don't want to explain why it works, and we will get to it, but at least you can believe that this kind of verifier can be described. And I want to show you that if this Turing machine halts, the value of all the games in the sequence is 1. Okay, so this is the easy part. Let's see it happens. So clearly, if M halts, and you take the nth game where n is greater or equal to t, the decider will do only step 1, will never get to step 2, and thus it will always give us 1. So the probability of winning this game is 1. We don't need the quantum value, we just need the value. Okay? So this is the easy part. So let me even highlight what I'm talking about right now. Why does this, why this doesn't work? Okay, so we talked about this point for all n greater or equal to t. Now the question is, what happens if you take some n, which is smaller than t, but is strictly, but for which 2 to the n is larger than t? The point is that as part of game of VNM, okay, you play VNM prime. Okay, this is part of doing Vn is doing n to the m n prime. So we go straight to 2 because we don't stop at t steps. We need we ran for less than t steps because n is smaller or equal to t. So we went to the second clause, but then we need to play the nth game of v prime. The point is that now we can use the compression. The value of the game 2 to the n, the original 2 to the n game, is the same as the value of the nm prime, right? Are you with me? So the value, I'll show what I'm saying now. Okay, so we know that in 2 to the n steps, the Turing machine halts. So the quantum value of the original v with entry 2 to the n, the 2 to the nth game of the original verifier is 1. But from that, and using compression, we can know that the nth game of the compressed verifier is also 1. But the value of the nth, the original nth game we saw now is just the value of the n game prime, so the new verifier's game, because the original game just simulates, just does like, it tells us do the compression and play the new nth game, so they have the same value. Okay, great. So we saw that also if the n is smaller than t, but t is smaller than 2 to the n, we also have value 1. But you can proceed by induction, like you can do this again and again.
Michael, what is the precise statement that the machine holds, the halts? Sorry?
If m halts, okay, so what did we get? We saw that if m halts, for any n greater or equal to 2, the quantum value of Vn is 1. The point is that you know it for n greater or equal to t. And you can use compression to deduce, and the fact that we the nth game calls the nth compressed game, okay? The nth game just calls the compressed nth game. So from that, you can use induction, compression and induction to deduce that actually for all n, the quantum value is 1. No matter, the point is that no matter how large t is, the quantum value of Vn is 1 for all n. This is the point that you need to take from this slide.
Michael?
Yes, Salam.
So, okay, you said that M1 will be our final game. So M1
n equals
will
2. Now I'll take n equals 2 because n equals 1 doesn't have any meaning when I take n to the lambda steps, right? So I need to choose this lambda such that.
Okay.
I start from, so, n starts from 2, but what is the point, Alon?
So you mean that, so this final Turing machine, assuming I believe you somehow this is a true game, it will have a so it will just have a constant running time, like, right? You just have...
Okay, so the point is that, okay, so I don't want to go too fast, but at least for now, we generated a sequence of games with the following property. if the Turing machine halts, all the games have value 1. You agree with that claim?
Yes.
Yeah, great. So let's move along. Let's see the second claim because it's a bit harder. Okay, so now let's assume that the Turing machine does not halt. Okay, this means that we always go to clause number 2, right? Like the Turing machine for any n, the Turing machine will go to the second clause. It will just simulate the compressed game. So again, winning, it is as hard. If you can win the compressed game, you can win the original game, and vice versa with the same entry. Like this is the point. Like the quantum value of the compressed game and the original game at the nth value are the same, exactly because the nth game just simulates the compressed game at the nth value. Okay, so but what do we know? We know that the nth game. So if actually the nth game now is just doing the compressed game, we need the same amount of entanglement to win the nth game as the compressed nth game. So this e to the vnm, okay, is the same as e to the vn to the m prime half. So to win, we need at least the same amount of entanglement, because actually we play the simulated nth game, the compressed nth game. Okay, but what does it mean? It means that we know by compression that the simulated nth game needs at least as much entanglement as the 2 to the nth game, or 2 to the 2 to the n, whatever is larger. Okay, but what do we get? We get here that the amount of entanglement needed to win the nth game is at least the amount needed to win the 2 to the nth game, which is at least the amount of winning the 2 to the 2 to the nth game. And all of these are also bounded from below. Okay, so this is bounded from below by 2 to the n, and this is bounded from below by 2 to the 2 to the n, and the next one is bounded from below by 2 to the 2 to the 2 to the n. And this just means that there is no amount of entanglement that enables you to win this game with probability larger than 1/2.
Wait, why is the first one? Is the first one bounded from below by 2 to the n?
Okay, so this is there is some ping pong thing here. Okay, so there is this e of vn. This is large n. You have e of vnm, all with 1/2. So I'm dropping the 1/2. I claim now that this is equal because it just simulates. The way we define this game is that this just simulates the n, the compressed verifier, the nth game of the compressed verifier, right? Itai, you are talking with me, right?
I mean, isn't it always the other way around, that the compressed verifier simulates the original game?
Yeah, but I defined here a decider that what it does, it runs the Turing machine. And if the Turing machine did not halt in the amount of time I let it run, it just simulates it just compresses the game.
Okay, I'm just saying like this equality is okay, but it's the other way around. This
equality depends on the way we defined VM. It's not true for general verifiers. It's true only for this specific verifier. So it is because you go to the second clause here and you use you move along to the second condition because the Turing machine never halts. So no matter what n is, you are in the second condition here.
Okay, I missed that completely. Okay.
Yeah, so we are under the assumption that m does not halt. When m halted, we saw that the value of the game is 1. You need, you maybe need large entanglement, but the value of the game is 1. Here we are claiming that the value of the game is bounded from 1/2. So the way we do it is the following. The amount of entanglement needed for Vn is the same as Vn prime. This is because of clause number 2. You simulate what the Dn does is just simulate Dn prime, right? This is just what is written here. Okay, but we saw that this is larger or equal to E of V2 to the n. M. Maybe larger V. Which is the same as E V2 to the n M prime. but this is larger or equal to EV2 to the 2 to the n m, which is equal to and all the equals are because of the second clause here, and all of the larger equals are because of the compression theorem. So the compression theorem gives us, so this is, maybe I'll write it in red. This is compression, this thing, and this thing, and this is clause to this thing, this thing, this thing. So the way we constructed VM enables us to say that the equalities hold, and the fact that we used compression implies that we can use the greater or equal. But the point is that the compression didn't say only that you are larger or equal to this number. You are also, all these, all the terms here are also larger or equal to 2 to the 2 to the entry of the, like the amount of steps you took to the right, right? So the number of 2, so it's 2 to the 2 to the 2 to the 2 to the n, where the number of 2s depends only on the on how to the right you are. But this just means that this number cannot be finite. This is an infinite number. It's not an infinite number, it's just infinity. You cannot win this game, the conclusion, you cannot win this game with probability larger using quantum and correlations, with probability larger or equal to 1/2. This is the conclusion. But this is exactly what we wanted. We saw that the value of the game. So this, and this is for every n. We didn't say anything about n. So for every n, the value of the game is bounded from above by 1/2.
Where did we use the fact that we chose exponential growth? What happened if we chose, if we went for, I don't know, polynomial growth?
Yes, so we need some super polynomial growth here. I don't think we need exponential. We had a bit of a discussion about this point at the end last time. Okay, so
whatever you need, I don't think you need it from here. You need it because because you want this algorithm to somehow reach an ending and not repeat infinitely. But for this particular argument, even going from n to n+1 would work, I think.
Yeah, this is true. This is true.
So again,
like this argument does not need the exponential.
Okay, that makes me feel better.
Okay, so I stated last time that Henry Wen is saying just the n and n+1, and I claim that he's a bit lying, but he's not lying. He's saying that the new game runs in polylog time. So you can think of the compression as instead of going, like instead of calling v prime n, you can call the thing that I called v prime n, he's calling v prime log n+1.
Sorry,
okay, and then he gets Henry Wen, one of the
but for
professors
this,
who
we only need to go to a larger number. Doesn't n+1 is
yeah, for this specific argument, you just need n to go to n+1 at
so
least.
Where is this choice going to affect us, or
which choice?
Going to exponential.
This is just true. I think any super polynomial will work. Like we will follow the proof. And
Why? But why not n goes to n+1? Where would they say hurt us?
So as Guy said, I think that the way you define the algorithm here, the fact that the nth game is simulating the compressed nth game will be important.
Okay.
Actually, Michael, you still have to convince us that this definition is fine because it's self-referential.
Right. It's self-referential. You need some.
Yes.
Okay. So for computer scientists, like they are used to see these kinds of definitions, but you need to say something. The fact that I said that it's always a lambda verifier. Okay, let's think of it for a moment. Okay, so you compress, and maybe like the compressed algorithm is compressing again, and maybe it compresses again, but you always get a lambda verifier. And we said that lambda verifiers, I hope I write verifier correctly, lambda verifiers, the description of a lambda verifier is bounded by lambda. this means that you will get into a loop. Okay, so you will compress and compress and compress, and at some point you will play the same game that you already played. Okay, because you are running a Turing machine which is bounded by terms of this lambda. So you are like, you cannot iterate too many times. And this is highly related to the fact that you use these lambda verifiers, that you give some bound on the description of these verifiers. And like, if I did it in a more precise way, I will define two Turing machines. Okay, and one will simulate another, and then you take the description of the one and you input it into itself, and then like you can do it in a more precise way. But at least I gave you the idea here. I don't know how to be precise now. It makes things quite more complicated notationally, and like you need to say something again about the self-reference.
It does follow from the recursion theorem, right?
Yeah, Kleen's recursion theorem. This is like the thing I need to name drop here.
So sorry, whose recursion theorem?
Kleen's.
Actually, Kleene.
Kleene? Ah, it's
yeah.
Kleene. Sorry, I thought it's clean. Okay, thanks. Kleene's recursion theorem.
Clean is clean recursion theorem. Never mind, it's a joke. Yeah.
Okay. Okay, so let me just say a few more words and then we'll take a break. So what did we get? Okay, so the conclusion. So if you take the game V2, you don't need to take any. So actually, if you go through the proof, you cannot take V2. You need to take V of some constant, which is universal. But at least the way I presented it, assume as if you can take V of 2 and everything works for it. And what V2 satisfy? It satisfies the following. If the Turing machine halts, the value of it is 1. And if the Turing machine does not halt, the value of it is bounded away from 1/2. And this V2 has a finite description. Like it's a finite being. It is bounded by 2 to the lambda. The description of it is bounded by 2 to the lambda. Its running time is bounded by 2 to the lambda. And that's it. Like you, this is a game that if you can decide whether it has value 1 or value smaller than 1/2, you will know whether the Turing machine halts. But we know that we cannot even say whether a specific Turing machine. Okay, so for some Turing machine we can say, but not for every Turing machine we can say whether it halts or not. So it means that not for every game we can decide whether it has value 1 or value bounded from 1/2, from above from 1/2. So deciding whether a Turing machine halts lives inside MIP star. Great. So I think we'll take, as usual, a break until 5, and we are still here. We can talk to one another. I will say that the next thing I want to talk is like how do you prove the compression theorem? Like it will be the second hour and also probably the next lecture and maybe even the one after that, but I'm not sure. It depends on how fast we'll go through this.
Where does the entanglement go into the argument?
Say again, Antti?
Where does the entanglement go into this argument?
This is a good question that I try to explain to Eyal at least what happens here. Like, okay, so if you know, like in all the early results of PCP, you had these kind of tests which were line versus point and plane versus point, right? So for checking that you are given a low degree polynomial.
Yes.
So I will, there is a way, and this I will talk about it today. You can just, for any number you want, you can, in poly n time, can make the provers share 2 to the n entangled bits. Okay? So this automatically means that you can just, I can play with you a game that if you want to win it, you must use lots of entanglements, like exponentially more entanglement than the amount of, like the size of questions I'm sending you, okay?
because I don't understand where the argument that you just gave us says anything but, you know, if you can always reduce the runtime by 1, then you can solve the whole thing.
But how can you?
No. I mean, I'm coming back to this. You know, why is there exponential? Why is there bounded entanglement? Here is a statement. You know, if any program you have, you can run it with 1 step less, then you can do a whole thing. I think I don't see which is you know, the same.
Up to some bound, right? But every large enough.
Up to nothing. You know, it starts from 100. That doesn't matter. Any program that you can run in time n, if you can make it run in time n-1.
But this is just known to not be true, Nati. Like you,
okay.
There are programs that you cannot run in n-1 time.
No, fine. But I don't see where the previous argument is doing. I mean, what I say is correct and trivial, right? Because it's like if 0 equals 1.
No, so I think the point that. Say again, nothing.
No, somehow you know, we didn't speak about entanglement. So why is what we just saw different than the statement that I just made?
Okay, Nati, I think I can tell you the following thing. No matter how succinctly you give me a graph, they can decide in some bounded time whether this graph is 3-colorable or not. If MIP, like using MIP star. Okay, for example, like this is the kind of result that they get here.
So
if you can distinguish between value 1 and value 1/2, you can decide, no matter how succinctly you give me a graph, you can take a circuit that defines a circuit, that defines a circuit, that defines a circuit, and you get exponential growth at each point, and that defines the graph. And for this graph, you can tell me in bounded time, but using lots of entanglement, whether it's 3-colorable or not. This is the kind of idea you need to think is happening here. Okay? And there is a bound, like there is a uniform bound on the amount of time you need to run this thing.
Michael, if I understand correctly, Nati doesn't ask how you prove the compression. He asked about how you used the compression to show that the problem is in that you can reduce
that R is in MIP star.
Again. So can you move to a slide before?
Yeah, great.
So you see, Nati, so the proof talks about entanglement. It tells you that the entanglement needed to solve Vn is at least the entanglement needed to solve V2 to the n. Right? This epsilon is the amount of entanglement the two provers use. Right? And this is impossible, right? Because this means, and this epsilon V2 to the n is in fact, it's the minimum between V2 to the n and 2 to the n. Right?
Max.
It's the no.
Yeah, it is at least both of them. This is the point.
Right. Right. So it's at least 2 to the n and then at least 2 to the okay, yeah, it's at least both of them, right? Let's say, right. But it grows, each time it grows, right? So this means this is just impossible. It means that it must take infinite number of qubits to win the game. And therefore, by definition,
maybe even infinite number doesn't suffice, but
it doesn't.
You just it depends. It might suffice, but any finite number does not suffice to win with the.
But you exactly said that the closure of CQ is the same as the closure of CQS, no? So if you can, I mean, you implicitly use this here, that if the quantum spatial value is greater than 1/2, by the way, I also wanted to say something about this, that if somehow using infinite qubits,
what
you
does
said that
infinite entanglement means? Okay, so if you use the tensor product model, you are right, but you can also use the quantum commuting model and say that there you have
quantum commuting.
But this
you are not using this quantum commuting model.
Right. I'm using the quantum, which is only finite dimensional spaces, and I'm forgetting the quantum spatial. You are correct. When I'm talking about Zilson's problem, I want to discuss this quantum spatial correlations and quantum approximated correlation and so on. But here in this discussion, I allow them only to use finite dimensional spaces. And there is some
even if you
limiting process here saying that you maybe can use larger and larger dimensions of Hilbert spaces and get larger and larger values, but we just stated that at least for this game, you don't. And
but not with the tensor product model.
You are correct that because of the things we talked about, like the topological things we said about the correlation sets, we can deduce from that even using the quantum spatial model, you cannot win with a probability larger than 1/2. This is true.
Sorry, so because I don't remember what is the quantum spatial thing.
The tensor product model with maybe infinite dimensional Hilbert spaces on both sides. So you take POVMs, you take tensor, so HA tensor HB, right? Yes. This is like box A's Hilbert space, and this is box B's Hilbert space. Now they're infinite dimensional, and you still take POVMs from here and POVMs from here.
I see. So even in that model, you cannot.
This game is still its value. If the Turing machine does not halt, the value of this game is bounded away from 1/2, even for this model. And this is Alon said that the topological arguments from
I see.
talk about Searleson problem.
I see, which means that that even in MIP, I don't know, star or whatever.
Okay, so the point is exactly that MIP star and what you just called MIP star are the same.
Yes.
Yeah, it's the same thing.
Yeah, but okay, because I have a question, which is this MIP whatever so you're saying so it's a general thing, this MIP star and MIP.
Yeah, you can approximate any infinite dimensional correlation using finite dimensional one. So in the sense of separating between with a constant gap, you don't care, right? You just approximate this one with something 1/3 the constant gap and the other with 1/3 the constant gap, and you are done.
So maybe continuing this a bit further in spirit of Searleson's problem, I think maybe the authors asked this, I don't remember, but you can also, so you told me now that deciding like the gap problem for this closed correlation set of all quantum approximated correlations, this is as hard as RE. But what about CQA? I mean, this is another closed set. Do the authors say anything?
CQA is the same as like the value of val Q.
No, the value on CQA and CQS is different.
No. Val Q is equal to val QS. Why? Again, my computer started to run very slowly. I don't know why. Okay, equal to val QS, which is equal to val QA. Because I defined the value using a supremum.
Sorry, I meant CQC. I'm sorry, I said the wrong thing. I'm asking about deciding CQC.
Yeah, so deciding CQC, they ask whether it's... okay, so Michael Benor said maybe 2 or 3 times ago that this is completely open, like nothing is known, not known, no lower bound or upper bound is known on for given a game, decide whether the Q gap problem for the QC gap problem, okay? The quantum commuting gap problem is completely open. And in the paper, they ask whether maybe it's complete for, it's known. Okay, so there is some upper bound known. It is in the complement of RE. Because we said last time that, not last time, okay, in some previous time, that there is an algorithm that approximates it from above, right? So deciding whether it's a no instance is, if it is a no instance, you can decide it in a finite amount of time. So this class is called the complement. Yeah, exactly. This is called the complement of RE, which is denoted co-RE. So they ask whether maybe they, I don't know if they have any. Okay, it would be nice if this is a complete question, a complete problem for co-RE. But as I understood from Michael, it sounds like there is no evidence that, at least for now, maybe there will come some evidence, but at least for now, there is no evidence that this should be true.
Just the fact that I don't know doesn't say it's not no, of course.
Ah, okay, yeah, but you're okay. So you are an expert in this field, so you know.
Michael?
Yes.
One more idiotic question. The definition of D, if you can go one slide or 2 slides even before, definition of D and of V actually does not depend at all on X, Y, A, and B.
It does, because the compression, after you compress, the sampler samples questions and okay, like the compressed game have some questions and answers that need to be satisfied. So you're right, for the first clause, you don't care about X, Y, A, and B, but for the second one, you do.
Okay. And this is what allows the quantum value to be something that isn't 0 or 1, right?
Yeah.
Because otherwise you will either say 0 or 1, and this compression allows you to get intermediate values, but the compression theorem says that you won't go above 1/2 if you start with 0 and vice versa, right?
Yeah, exactly. This is a good point. Like if you would have run only the first clause, it would be either 0 or 1, depending only on whether the Turing machine halts in n steps.
Yes.
And for non-stop, non-halting Turing machines, it will be always 0, right? Yes. The point is, as you said right now, that given that clause 1 is always 0 for the non-halting Turing machines, you can bootstrap this thing and use it to, okay, not bootstrap, but you can use this fact to deduce that the quantum value of this game is bounded from something below 1. Like this 1/2 is just arbitrary, but
yeah, but
1/2.
By half by your definition.
And one more question: Is this bootstrapping, or however you'd call it, is this standard? Because I never seen it, but I'm not on computer science, so perhaps the problem is in my side.
I'm also not a computer scientist. I think this is not a standard thing because this is an amazing and original idea, but maybe they have some previous motivation. Michael, Guy.
Okay, well, perhaps I'll have to read about this Kleene theorem, and then I'll get more.
The recursion self.
The whole idea of recursively defining a self.
Okay, this comes from the halting problem itself, right? You know the proof that the halting problem is undecidable. Yeah, so the kind of taking something and taking it as the input of itself is very...
but it's different. It's different because there you explicitly define everything. You don't need this recursion.
Yeah,
you don't
so
define
I will... No, you do.
And count on this
here you do the same. You should think of it as the following. DM takes the description of some Turing machine. Okay, there is some Turing machine. It has some finite description. This Turing machine is doing this thing, but for a more general, like it takes a pair of Turing machines and it compresses one and simulates the other and something like that. And then you take the description of the thing that you get, okay? And you use it with itself. You take the description and you take it as the input. Okay, so this kind of trying to take the description of the Turing machine itself and using it as the input appears here as well, like the same as in the halting problem. Okay, maybe I will. If yeah, it's okay. Like I didn't give a precise way of defining the VM, right? Like it seems like VM is like the way I define it. It seems like why is it definable? Why is it a finite entity? Why like everything is completely not clear? But maybe if you want at the end, like at 5:45, I'll show it in the paper, like what is the precise way they do it. And then I believe it will be a bit more clear to you, okay?
Okay, sure. I say it's 5:03, so I won't stop you. Thank you.
Okay, cool. So I think I'll resume. I will not use Nati's method this time because we don't have lots of time. And I think we, like now, very nice mathematics gets inside. So I think I want to show you this thing, at least part of it today. Okay, so now I want to talk about the first ingredient of the compression theorem, which is called introspection. Okay, so the way we should think of introspection is the following. I tried to at least explain a bit about it before, but in the first hour, but now I want to like dive into it. So Babai, Fortneau, and Lund proved that the non-quantum deciding the classical value of a game is as hard as non-deterministic exponential time. Okay. Now you can take the protocol that they defined. Okay. So they take every language in NEXP and they define a game such that if so for any instance, for any natural number, they define a game such that if this natural number is in this language, then the classical value of the game is 1. And if this natural number is not in the language, the classical value is bounded away from 1/2. Okay, so this is what BFL did. But you can just think of this protocol scaled up. Okay, so instead of instead of deciding a language in NEXP, you try to decide a language in NIXP. So something that if I am given a doubly exponentially large proof, I would be able to believe that this is a true proof. Okay, so NIXP is just, for example, given a graph with a description which is polynomial, but maybe the graph is doubly exponential large, deciding whether this graph is free colorable or not. This is the kind of questions that are in NIXP. And you can just use the protocol of BFL for these kinds of questions. The problem is that the questions and answers are very long. Okay, so the questions are exponentially large and the answers are like, you need to ask questions that are exponentially large. You need to get answers that are exponentially large. Okay, so you need to read something exponentially large. So if you are a polynomial time being, you will not be able to even not send, like, you cannot send the questions, you cannot receive the questions. So this protocol, in some sense, is irrelevant, but the point is to somehow reduce the size of the questions and reduce the size of the answers. And this is a very important point. So I'm not sure, maybe if you are with me, there is in the participants this yes, no buttons. You can try to just push the yes button and I'll know that at least some of you are with me. So you push the participants and you just push the yes. Okay, so at least half of you are with me. This is good, so I'm moving along. Great, so the point is that now you want to somehow scale down the questions and the answers, and the way we do it is that the provers will need to pay with some entanglement. Like this is the method that we are going to use. And okay, so I'm going to now talk only about how can you reduce the questions. Okay, so the introspection part is just as it says. What is introspection? Making them do their question themselves. Okay, so instead of sending the idea is, okay, so let me write it as, see it here. So I had the long questions X and Y. So I would expect that I will send X to A and Y to B, and then they will answer with some small a small b here, and small a here. But these are very long, like this is long, this is exponential, this is exponential, this is exponential, and this is exponential. Now I'm going to change it a bit. I'm going to send polynomial sized questions, somehow send questions X prime and Y prime to A and B, and they will answer a tuple with a pair. not any tuple, with a pair, which is exactly x comma a, and b will answer y comma b. And the way I interpret now, like the answers are even longer. If their previous answers were exponential, now I have like a pair of exponential things. It's not much larger. It's, asymptotically, it's the same, but I enlarged the answers, but now at least the questions are short. And the way I interpret this is the following. Okay, if I'm sending x prime and y prime, a and b answer something like the following. If you would run the long protocol, the original protocol, which is exponentially large, you would have asked me x, and I would have answered a. Okay, so this is an important point. So
how does he know x from x prime? I'm confused.
Okay, so this is the point where they use very large entanglement. They measure. Okay, so the original protocol had some question distribution, right? Itai.
Yeah.
Okay, so if the original protocol had some question distribution, you want them to sample out of this distribution. So the x prime and y prime somehow forces them. It forces them to sample from the correct question distribution, right? And then if they sampled from the question distribution of the long protocol, they can also answer the long protocol, right?
Yeah, okay.
Okay, so in some sense, you delegate the sampling to the provers, but you need to check two things, okay? So if you delegated the sampling to the provers, you need to check that they actually sample from the correct distribution, right? So there is the distribution of questions of the large protocol. You need to check that they actually use this distribution, and also that they don't share any information. Like all the idea in these kind of protocols is that you send a question to Alice and a question to Bob, and they don't communicate, right? So the way they sample, you need to also check that they didn't share information that they are not allowed to share. Okay? Okay, I'll let you stare at this a bit more, and I'll say more words, and then hopefully it will create some discussion here. So as is written here, we said that we shortened the questions, but the answers are still long. If you know PCPs, you know that this is not such a big problem. So we'll do some PCP argument in the future, which will reduce the size of the answers. But at least for now, we only reduce the size of the question. So we don't care at all about the size of the answers. But there is a problem. How do you verify that they sample the correct distribution? And also, how do you verify that they don't share information that they are not allowed to share? And here, quantum mechanics gets inside in a very good way. Because in quantum mechanics, there is this notion of the Heisenberg's uncertainty principle. So you can measure your qubit with some basis that makes the other person lose all information about this qubit, each side of the qubit, okay? So it's not like if they are entangled, you can assume that they are entangled in some way, that if you measure this part in a bad basis, it will destroy the information in the other side. So the way that we will verify that the other prover didn't get information that it wasn't supposed to get is using Heisenberg's uncertainty principle. And I'll explain what it means, at least in our context. So it's a mouthful, but at least like the mathematical way of thinking of it will be very clear when we'll get to this point, which will be hopefully today. And the way that we check that they sample from the correct distribution is exactly the fact that they use these kinds of point versus line tests. So we assume that they sample a point and sample a line, and this is very linear algebra, and we will see that there is a way, if they share many EPR states, many EPR pairs, we can ensure that they actually use a point and the line that are chosen in the correct distribution. So let's see it in for a moment. So this is a very simplified example. For the actual compression theorem, you need a more general notion of these conditionally linear maps, and when we will get to the technical parts of the proof, we will talk about it a bit more, but I want to review at least the question distribution that interests us if you think that you only want to compress once, okay? Like if you just want, instead of solving a non-deterministic exponential time language, you want to decide non-deterministic doubly exponential time, NIXP, then you only need to compress this distribution. Okay, so as I mentioned, for the free coloring, the succinct free coloring problem, which is the complete language that you can think of used by Babai, Fortno, and Lund, what they do is just they tell you to, they code using, they use some coding of colorings, and these colorings are actually good colorings of the graph that is given, if and only if they satisfy two things. They need to be low degree polynomials, okay? So the coding is using polynomials, and these polynomials need to be low degree, whatever that means. So there is some bound on the degree, and they need to be under this bound. And also they need to satisfy some equation, and you generate some polynomial from the circuit that defines the graph, and you just check some arithmetic condition on these polynomials. And if all these polynomials satisfy, if there is such polynomial that satisfies all these things, it is related to a genuine free coloring of your original graph. And if there is no such low degree polynomial, you can deduce that there is no genuine free coloring of the graph. Okay, so this is the kind of argument that happens there. And the way that they check, so they define, the coding is defined over some large vector space. Okay, so here we have a vector space of like f2 to the t to some m, and you should think of m as being some log squared and t as being something like, I don't know, log of n or something like that. Okay, so the size of the input. Anyway, the way that you check that they actually gave you a low degree polynomial, okay, so they use even a multilinear polynomial, so just the power of every, okay, so the monoms are just of the form xi1, xi2, xik, where the like all the ij's are different from one another, so there are no powers here. I'm not allowing you to take this to some power and so on. Okay, later we will need powers, but at least for now, let's think of just these multilinear polynomials. And the way you check that this is actually a multilinear polynomial, like you give one player a line in your vector space, you give the other player a point on this line, you expect the line player to answer with one variable polynomial. So if you restrict the polynomial to this line, you get a polynomial with only one variable, okay? So the line player should answer with some restricted polynomial to this line, and the point player should answer just with a single output like that, and a number in f2 to the t. And you accept if and only if this number that the point player gave you is actually the evaluation of the polynomial that the line player gave you on this specific point. So this is the kind of idea you give them lines and points. They need to give you back polynomials. Okay, so if it's a 0-dimensional polynomial, it's just like a value, and on the line you get a one variable polynomial, a polynomial with one variable, which is low degree, and you accept if this actually is a low degree polynomial, if this evaluation is correct, and another condition. Any questions about this point? Because this is important. Guy, you wanted to say something?
No, I maybe can explain a little more, but I don't know if it's necessary.
Okay, so at least for now, the only thing, maybe if you can explain more about this, the following point, the only thing I care about is that they need to sample a point in the line. And the way they sample a point in the line is such that the line player does not know what is the specific point on the line that the point player gets, and the point player just know its point. It doesn't know what is the line. So this is the only thing I care here.
Maybe for people who don't know it, to get a little bit of intuition, I'll just say that there is this 3 coloring problem, which is lying behind there. But then it gets translated to a question about the existence of some low degree polynomial over this large space that has some properties. Now forget the other properties, just think of this low degree polynomial over a large space. If the provers can show the verifier the polynomial, and the verifier sees that it's actually a low degree polynomial, then we are done. But these are polynomials over a huge space, and the verifier doesn't have time to check that this is actually, that this function that is being shown is a polynomial. So to check
a low degree
polynomial. So to check that, he asks for one prover to give him an evaluation of this polynomial at a single point, and he asks the other prover to give him the evaluation of this polynomial on a line, on a whole line. Now, to check that a polynomial is of low degree on a line, that's easy. The verifier can do that. And to check that this line, you get a low degree polynomial, and this low degree polynomial gives on the point the same value as he got from the other prover. This, again, the verifier can check. And the nice thing is that if the two provers agree on some low degree polynomial, then of course they can answer these questions easily. But if they don't agree on one low degree polynomial, with high probability, the value that the verifier will get from one prover and the value that it will get from the other prover will be different on the point. And so the verifier will know that he's being lied to.
Yeah, with high probability, they cannot lose only on a small fraction of the question set. If they lose on some fraction of the question set, they lose on a large fraction of the question set. So there is some constant size, the constant amount of pairs.
But at least, yeah, could lie on, but never mind. That's the idea.
Yeah.
Right, so, but the point is that when you ask the line prover, he needs to answer about the whole line, and he doesn't know what point you asked the other guy, because if he knew, he would be able to cheat. And now you want the provers to generate the questions by themselves, but still not know what the others was, what was the question of the other, what was the point of the other.
Right. That's Thanks, Guy. This was a good explanation. This was good. Okay, so now this is our goal. So Guy gave us our goal. They need to, we need to make them.
How do they, Guy, how do they avoid cheating in this more
but
complicated.
this is what I'm going to explain, Nati.
Okay.
Like, this is my
okay.
This is my explanation.
Sorry.
Not mine, but at least for this talk, mine. Okay, so the way that we will verify that they not cheat is using Heisenberg's uncertainty principle. Okay, like this is the methodology. Okay, but how can they sample a point and a line in a way that is correlate? Like they need to correlate in some way, right? That this is exactly need to ring a bell, so they need to correlate in some way without sharing any information. And still, this one needs only to know of a line. This one needs only to know of a point, but the point needs to be on this line, right? Like so, the way we do it is that we force them to share this state. Okay, so we a state is just right, a unit vector in some tensor product Hilbert space. So there is some C to the something tensor C to the something, and we assume here that it's the same something. And we force them to win, like we play, there is a subroutine, there is a small game, and the rest of the talk will be about this small game that enables them to share this specific state. But what does this specific state do? If you measure it, if they measure it according to the same basis, so okay, so now they share this thing. So these are just 2 to the Tn+1 qubits that are fully entangled and are fully correlated. So if one of them is measured to be something and the other is measured with respect to the same basis, they will give the same answer. So this is what enables them to agree on the line and the point. So in the fact that the line is something and the point lies on the line. Okay, so there is this notion of measuring using the x basis and the z basis. So we have here c squared, like this is the tensor product of, like this c to the something is actually the tensor product of c squared a large amount of times. Wow. This is very stuck. Okay, and now what I will tell them to do is to measure, there is a way of forcing them to measure each of the qubits. Okay, so now they have many qubits that are fully entangled, and I can enforce them to measure each one of them, either according to the regular basis of c squared. Okay, so either according to this basis, and Guy explained, at least in the first or second lecture, that the way that I define the projective valued measure is just choosing a basis. So choosing a basis is the same as defining some measurement, defining some experiment that the provers need to do. So when I say that they measure according to the z basis, I mean this basis. And when I say that they are measuring according to the x basis, I mean this basis. Okay, so 45 degrees apart. And I can tell them, you now measure these many qubits according to the z basis. You measure these qubits according to the z basis. And the point is that sometimes I make them measure the same basis. So you should think of it as running the game, like there are many options of playing the game. I can now make them actually sample the point and the line, but sometimes I make one of them sample the point and the other need to hide something. So he will measure some other information according to the incompatible basis. So if you measure something according to the x basis, it erases all information according to the z basis and vice versa. This is exactly the Heisenberg uncertainty principle that we need here. Okay, so these are incompatible measurements. And using this fact, you can both make them be able to generate a point and a light that are matching one another, and sometimes hiding information from one another when they measure things according to the opposite basis. And if you do this carefully, if you generate such a game that sometimes measured according to the X basis, sometimes according to the Z basis, and so on, you can verify that they sampled, first of all, that they sampled a uniform line and the uniform point on this line, and that they didn't share information. They didn't check, they didn't measure some qubit that they didn't need to check. Like if you told them the point player, for example, okay, so what does the point player does? So you have, I don't know, an X and a V. Okay, so the first 2 to the T n qubits are,
Michael,
if you measure all of them according to the Z basis, this is the point. If you take all 2 to the T n second, the other 2 to the T n qubits, and you measure them according to the Z basis, this is the direction. So if you just measure everything according to the Z basis, you get both the point and the line. What we need to do is somehow check that the point player only read the X part, and the line player somehow read enough out of X and V such that it doesn't know nothing specific about X, except that it is on the line that it got.
Michael, let me just add what you really want them to sample and do that the way we want. The thing is that even if you're sure that they're doing it honestly, that they will follow your direction, they need a way to do that. And that they can do by measuring in incompatible bases in order to hide information. Then we'll check that they really need to do that. So I think that shows, because we need to let them do it. And the way to be able to do it, even if we are sure that they're following the protocol, is by the method you just suggested. Then we'll also check that they're really doing it.
Yeah, and the way we check it is by constructing some game that, like any pair of questions in this game, either checks that they hide information or checks that they are actually compatible. Like, okay, great. So at least this is the idea. Okay, so I want to demonstrate it in the following example. Okay, so assume this direction is just E1. Okay, so we have some vector space. There is the first element of the basis in which this vector space is given to us. I call it E1. So I assume that the line is just parallel to the first axis of this space under the basis that I'm given. So what I need to check is I need to check that the first player only measures according to the Z basis the 2 to the T and first coordinates, because this will tell him what is the point. And how do I check that the line player doesn't lie to me? I tell him measure everything according to the Z according to the Z measurement, and just don't measure the first coordinate, right? Don't measure the first qubit, the first T qubits, okay? Because the first T qubits will tell me what is the value in the E1 coordinate, and this is exactly what I'm trying to hide from the line player. So how will I hide it? I will just tell the point player to sometimes measure these T coordinates according to the X basis. Okay, so this is an example, a very simple situation in which you can hide the point from the line player. So, and then the line player will lose all information about the first T qubits according to the Z basis, and then he will genuinely only know the line and will not know the point. So if he will check what is the coordinates in the first T qubits, like what are the first T qubits, if it will measure it using the Z basis, he will get a uniform answer out of all possible strings of T bits. Okay. Okay, so I think at least you got the idea here. So there are these incompatible bases, and using these either compatible or incompatible bases, I can ensure that they either are compatible with one another or otherwise hide the needed information from one another. Okay, but I just stated that first of all, I need to force them to share many EPR pairs, these 1, 0, tensor 1, 0 plus 0, 1, tensor 0, 1. I somehow need to ensure that using only polynomial sized questions, right? I need to ask them polynomial sized questions, but they need to share. So let's look at it again. They need to share exponentially many qubits, right? So using polynomially large, polynomial sized questions, I need to ensure that they share exponentially many qubits. So at the end of, like in the following 10 minutes and probably the following first hour of the next lecture, I'm going to explain at least how you can force them to share a single EPR pair. Okay, let me show you that there is a game that forces them to share a single EPR pair. What happened? What happened there? I don't know, but I'll try to share again, and hopefully it will not happen again. Okay, great. So now you know what is the motivation for the next hour is. Whoa. Great. So now I want to talk about self-testing, this notion of playing a game such that if they want to win this game with high probability, they must share many EPR pairs. Okay, this is like the end goal, but at least for now, let me show you that if two players are playing the CHSH game with optimal play, like the best strategy possible, they must share at least one pair of EPR, one EPR pair. Like this is a nice start. And we will see the fact that this will be very hard mathematically will explain why this is a very technical part of the MIP star is equal to RE proof. So showing that you can enforce them to share many EPR pairs is quite technical and heavy in details. But I think that the example that I brought here is quite nice. So hopefully you will enjoy what we are going to see now. And I'll just remark, because probably I will not get to it, that this is very related to what's called stability of groups. So we will see that the fact that you can show that finite groups are stable in some sense enables you to check that the players share many EPR pairs. So this is just a teaser for those of you who come from group stability. Great, so let's recall what the CHSH game. Now we go into something that is purely linear algebra. So if you weren't with me for the last 30 minutes, you can just come along again and go back and feel nice and that you understand all the mathematics and so on. So what is the CHSH game? All the questions and answers are just single bits. So IA is IB is OA is OB is just the field of two elements. The question, you sample questions uniformly. So you send either a 0, 0, 0, 1, 1, 0, 0, or 1, 1 with equal probability. And you win, the players win if and only if this condition holds in the field with two elements. So if and only if the sum of their answers is the same as the product of the questions. Okay, so this is almost the simplest game you can think of. And we now assume we at least, I'm not going to prove it now, but we said that Cyrilson proved that this number is the best winning probability in this game using quantum using quantum correlations, you cannot win with probability higher than this number. So let's assume the players have some strategy. So they have these measurements, these POVM, so M00, M01, M10, and M11 are positive operators. So these are just non-negative semi-definite matrices that sum up to the identity. So these two sum up to the identity, and these two sum up to the identity. And also player B has the same. So he also has 4 matrices. The first two sum up to the identity. The two others sum up to the identity. And also they share some unit vector inside C to the D tensor C to the D. So these M's and N's are D by D matrices. Okay, so all the information is here in the slide. And we assume that if they play the game using these measurements as we define them in the first few lectures, then they win with this exact probability. So they win with the maximal possible probability. The point is that we will show that there exists some isometry of C to the D such that actually psi, so we will see that there exists some isometry, 2 isometries, okay? So isometries of C to the D such that if you apply, so isometry is phi and phi prime, such that if you apply phi tensor phi prime on psi, you just get EPR pair tensor rubbish. I hope I wrote rubbish correctly. Probably not. So, if you act with the same isometries on the matrices, we will see that the matrices only act, they do nothing to the rubbish part. They only act on the EPR pair. And in this sense, you checked that actually to win this game, you must share an EPR pair. Okay, so this is the kind of idea behind self-testing. Okay, great. So we know at least where we are going to. And to do that, I defined something that I call a pre-observable. The reason I call it a pre-observable and not an observable is whether if these M's and N's, so if the M's and N's are projectors, so if Mij squared is equal to Mij, which is equal to Mij conjugate, okay, so then these things are unitaries. This is a unitary. And when it is a unitary, I will call it an observable. But when these are just positive matrices, these are not necessarily unitaries. Okay, so the name observable will be reserved only to unitary matrices. And these pre-observables are called pre-observables exactly because when they are projectors, when the strategy is actually a projective valued measure and not a positive operator valued measure, these are genuine observables. Great.
Sorry, I don't understand. If M00 and M10
are projectors.
M01,
okay, so let's see that.
If
this
they
is a
are
good
projectors, their difference is still not even positive.
They should be mutually orthogonal.
Okay, okay, so let's check that everything. This is a good calculation, and we can finish with this. The guy's question is very good. Why, when M00 and M01 are projectors, and the point is, and sum up to the identity, and this is exactly the important point, then the difference between them is a unitary. So let's check that this is true. This is quite a straightforward calculation. So the point is that we know that M00 plus M01 is just the identity. What is a reflection? Right. You're correct. This is a this is an order 2 unitary. So all its eigenvalues are just plus minus 1. Right? Because the fact that they sum up to the identity and both of them are projectors implies that actually these are projectors on complement, on orthogonal and complement subspaces of your vector space. So this is just an orthogonal decomposition of your vector space into two subspaces, and M00 is projecting on one of them, and M01 is projecting on the other one. So actually, you can deduce from this thing that M00 times M01 is 0, and vice versa. Okay, so from that fact and the fact that they are projectors, you can deduce that they are their product is 0, and they are the fact that they are projectors means that they are self-adjoint. So this A0 is self-adjoint, and A0 squared is just the identity. Okay, so you can just check that when you take this thing. So this exactly means that this A0 has only eigenvalues plus or minus 1, which exactly means that it's in a unitary, which is also of order 2.
You verify this by squaring, right?
Yeah, exactly, right, exactly. Both of them. Also the first condition you verify by squaring. Okay, great. So I think we will finish here, but as I said, our motivation is to keep analyzing this CHSH game up until we see that there exist these two isometries such that actually if you take the original state that they used, it is actually an EPR pair tensor, something that you don't care about. And the measurements only act on the EPR pairs and pair and not on the rubbish part.
Okay.
Okay, thank you.
Thank you.
You're welcome. So the next, you're welcome. Next meeting, linear algebra.
By the way, Michael, I think there are 2 typos in the slides.
Just send them to me by email. I will.
Okay.
I will correct them. There were many typos, and just feel free to send me corrections via email.
Okay. Thank you.
You're welcome.
Bye.
Bye-bye. Thank you.
Bye-bye.